An ionic bond is a strong charge interaction in which one atom has accepted one or more electrons and therefore is negatively charged, and another atom has lost electrons and is therefore positively charged. For example, sodium, which has 11 protons and 11 neutrons, has a filled 1s shell, filled 2s and 3p orbitals, and then has one extra electron in the outermost shell. And that electron is very easily lost. That electron is easily picked up by another element, another atom that is more electronegative, such as chloride, which has 17 protons, 17 neutrons, filled 1s, filled 2s and 3p orbitals, and almost filled the next ring. That electron can easily be added to a chloride, filling that outermost shell. Therefore, you end up with a sodium that is positively charged. It's got one extra proton relative to its 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons, and a chloride that is negatively charged. It has 17 protons and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, plus the extra 18, so negatively charged. And those strong charges, opposites attract, and so you wind up with sodium chloride. Potassium, which has 19 protons, 19 neutrons, and 19 electrons, therefore 2 more protons and 2 more electrons than chloride, it fills up that shell with 18 and then has one extra electron. And so potassium, K, also loses an electron to make K+, which would repel a sodium but attract a chloride. Calcium, which has 20 protons, 20 neutrons, easily loses 2 electrons to become Ca++ and can attract 2 Cl minuses, or calcium chloride. Ionic bonds are very strong when there are no other charges around, but ionic bonds become weak in water. Ionic bonds in proteins and other biological molecules can be stable or unstable depending upon whether water or other charged molecules, other ions, can get to them. I'll draw a protein. Each of these circles is an amino acid with peptide bonds between the amino acids. And I'll draw two situations. One in which we have a positive charge and a negative charge in a part of the protein that is so wrapped around that water cannot fit, cannot get at. The ionic bond, in that case, the ionic bond between these two is going to be very stable. But between the ionic bond, it's very easy for water to get in. In that case, the oxygens that are slightly more negative will be able to get near to the positive charge, and hydrogens that are slightly more positive can get near to the negative charge and cause these to separate. The negative charge is surrounded by a hydration shell in which the hydrogens are closer to it, and the positive charge is surrounded by a hydration shell in which the oxygens are closer to it. Therefore, this ionic bond is not going to be very stable. With this ionic bond, we'd expect this amino acid to be able to go back and forth very easily, because whenever water happens to be close by, it disrupts that ionic bond, but there still is a negative and a positive charge, and if these swing close enough together, they'll be attracted to each other. So we have a stable ionic bond, protected from water and other charges, and an unstable one that's easily pulled apart.